Look at a couple of other examples where we take a limit. This time we're going to go as x goes to infinity. So the upper limit is going to be infinity. And so we're going to take the integral from 1 to infinity of 1 over x squared dx. So by definition, that's the limit as c approaches infinity of the integral from 1 to c of 1 over x squared dx, if such thing actually exists. Now we know that if we go from 1 to c, 1 over x squared is actually defined and continuous everywhere, so that integral definitely does exist, and not only that, we can find it. 1 over x squared is just x to the negative 2. We can use the power rule, add 1 to the power, that becomes negative 1, multiplied by the reciprocal of the new power, which is negative 1 here. Then we evaluate from 1 to c. I'm going to rewrite that as x to the negative 1 is 1 over x. And then evaluate for c, it's negative 1 over c, minus, and then evaluate at 1, minus a negative 1 over 1. Well, 1 over 1 is 1. Those two negatives makes a positive 1. So we got 1, positive 1, and then minus 1 over c. And if we take the limit as c goes to 0, the 1 over limit goes as c goes to infinity, the 1 over c then goes to 0, and the whole thing goes to 1. So here we have a picture. Here is 1 over x squared, is the top of this curve. Here's x equals 1. This is our boundary here. It goes up to the point 1, 1 right there at our corner. Corner down here at 1, 0. So there's a line segment of length 1 for that side. The bottom is an infinitely long line array, actually, part of a line going from 1 to infinity, and the top of the curve starting here at 1, 1 and coming down concave up has an infinite length as well. So this definitely has an infinite perimeter, but it just works out that we do get a finite area. In fact, it's exactly one tile for this. That goes on forever. You couldn't actually build this thing physically because you can't actually go on forever, but if you could, you'd only need one square tile to do it, but an infinite perimeter. Now, before you start thinking that everything is going to converge, here's one that does not converge. We take the integral from 1 to infinity of 1 over x dx. Looks very similar to the one up there. 1 over x does approach 0 as x goes to infinity. That gives us some hope that this might work out. Let's see what happens. Very similar to the last problem. The integral from 1 to infinity of 1 over x dx, by definition, is the limit as c approaches infinity of the integral from 1 to c of 1 over x dx. 1 over x is x to the negative 1. We apply our rule here, but the antiderivative of 1 over x, or x to the negative 1, whichever one of these ways you think of it, it's the natural logarithm of x. Actually, that actually should say the natural logarithm of the absolute value of x. Although, of course, it doesn't really matter, because if you're a number between 1, c is above 1, so it's definitely positive. Both 1 and c and all the values in between are positive. So the absolute value could be dropped. So this becomes the log of c minus the log of 1. Log of 1 is 0. And so we get the limit as c goes to infinity of log of c. But we know that the logarithm function does grow without bound. So in fact, the logarithm, this limit of this logarithm is infinity. So we say that this integral diverges to infinity, indicating that we have an infinite area. Now this blue curve is 1 over x squared that we just looked at earlier, but the purple curve now is 1 over x. And certainly you see that's a larger area right here, but of course this far out they're both finite. If we go on to infinity, the purple area would be infinite, and the area under the blue curve is finite. It's only 1. So it doesn't look like there'd be that big a difference, but it does turn out to be a big difference in certain cases. So in fact, that's kind of an interesting result there. In fact, the purple one is kind of the one that makes more sense in one way, because it has a infinite perimeter and an infinite area. It's kind of the other one that's kind of unusual, is this blue one here, which has an infinite perimeter and a finite area. So that limit may or may not exist. In this case, the limit diverges to infinity, so we would say this does in some sense represent an infinite-sized area. So the only way you're going to get this to work out, okay, and get a let's see, get a function that is going to have a finite area, something like this, if we're going out to red infinity, is this thing is the function is going to have to approach the x-axis. Say if it was approaching some value up here, you can clearly see that if it was approaching a horizontal line up here or going off to infinity or something, you could clearly see that that's going to be an infinite area. But in this case, the only way you're going to possibly have this happen is if the function approaches the x-axis. Okay, but as we see, even that's not necessarily enough. You have to just kind of work this out and see what happens. Okay, we'll stop there on this video.